I'm very pleased to present these results today, where we are really trying to contribute into the topics of the previous presentation and try to include pore fluid pressure evolution and viscoelasticity on earthquake cycle simulations. So, as we have seen in the previous presentation, there is a general interest in understanding how geologic faults respond to the transient source of fluids. And this can be a problem that we can see on natural faults when we have the percolation of fluids on faults, and we have various processes such as seismic swarms or aftershock sequences. And we can see also the interaction between fluids in subduction zones, where we have the full spectrum between seismic events and slow slip events in the down deep region of the megathrust. But this problem is also related to anthropogenic scenarios of fluid injection, such as geothermal exploration, CO2 sequestration, and simply injection of fluids on faults. So when we take the example of subduction zones, we know that we have a depth varying behavior. So we can have the more shallow portion of the megathrust, we can have the seismogenic zone, where we have moderate to large earthquakes. And going at depth, we have this interaction with slow slip events and tremors. These two regions are located close to each other, and we have examples where there is an interplay between these two regions. And earthquakes can cause slow slip events, and the other way around, the slow slip events can instead trigger an earthquake. And possibly the two main mechanisms that are related to these processes are temperature-dependent rheology and the presence of fluids, in particular due to processes that are also thermally activated, such as dehydration. Now, when we think about subduction megathrust, we typically assume that the pore fluid pressure down there is very high. And therefore, the effective pressure, the effective normal stress is very small. And we have different studies where this has been applied, either for experimental studies or numerical simulations, where the effective normal stress is very small, of the order of 5 to 10 megapascal. And the reason why we can have this low permeability and the presence of high pore fluid pressure can be because of different mechanisms, such as serpentinization, which cause an increase of volume and a decrease in the connectivity between pores, and deposits of silica, and the stacking of all the shear zones. And because of that, we can have a chronic region of the megathrust that is always with high pore fluid pressure. And therefore, this has been one of the justification that to assume a high pore fluid pressure in friction models, particularly in order to reproduce realistic properties of slow slip events. And here you can see a list of studies, but of course there are even more studies of that. More recently, we have also some observations from oceanic bottom seismic network, where we have a fluctuation of pore fluid pressure. And I think this is one of the key observations that are telling us that pore fluid pressure can indeed be very high, but at the same time is also changing over the seismic cycle, or even within one single event. And these observations are indeed telling us that the pore fluid pressure is a dynamic quantity that is weakening the fault, but is also playing an active role in earthquake source processes over the earthquake cycle timescales. So for this reason, we decided to develop a new hydromechanical earthquake cycle code. This is a 2D continuum-based finite difference code, and here you can see one of the governing equations that we solved, the conservation of total momentum for the solid matrix and fluid. And this code solves also the acceleration term. So we also take into account the inertial term that was broadly discussed by Nadia in the previous presentation. And in particular, in this case, we assume that the acceleration term refers to the acceleration of the solid part. We neglect the difference in the acceleration between the solid and fluid. And this is the type of inertial term that we take into account. Then the other governing equations that we solve are the fluid momentum, where we have the ratio between the permeability and the fluid viscosity. And then we take into account the fully compressible solid mass, where we have the drain bulk modulus, the Biot-Willis coefficient, and also the compaction viscosity, which is an important component of our simulations, which I will show later, can control the pressurization mechanism within the fault zone. And finally, we also solve for the fully compressible fluid mass, where we have the Skempton coefficient. And in this way, we can have a fully coupled system that is also fully compressible. These type of simulations also take into account the linear viscoelastoplastic rheology. In this particular case, we don't solve for temperature and we assume a linear viscosity. We will do that in the future, but in the development of this code, we were mostly focused on implementing the pore-elastic properties. And at the moment, with our simulations, we are simulating a Newton viscosity, where we have in series the viscous, elastic, and plastic component. In this presentation, I would like to discuss two plasticity models that we are currently testing. The first one is the well-known rate and state dependent friction. This is the typical evolution of friction that we take into account in earthquake cycle simulations. The main difference compared to the classic formulation of rate and state friction is that our code is a continuum-based model, and therefore we have invariant quantities inside our system. So in this case, we don't take into account the effective normal stress, but the effective pressure, which is the results of the total and fluid pressure. And the formulation that you see here is the so-called regularized version that is typically assumed for seismic cycle simulations. In particular, we also account for the aging law for the evolution of the so-called state variable. And we also take into account the evolution of the latency and compaction following the studies that have been proposed in the past, and first from Seagal and Rice in 1995, motivated by the experiments of Marone et al. In 1990, where basically we are taking into account the evolution of porosity with shearing. We try to test this type of simulations in a simple model. Here is the setup where we have an antiplane motion with a planar fault and with a finite fault thickness. These type of simulations have a velocity strengthening patches on the left and the right side of the model, while we assume a velocity weakening patch in the middle. And from there, we simply try to impose some permeability barriers by assuming with some constant wavelength, some permeability barriers where will result in high pore pressure. And we try to study the interaction between the so-called seismic barrier and the barriers that instead have low permeability, which will result in high pore pressure and low effective normal stress, and therefore they are typically patches that they creep over time. And we try to, in this study, we try to simulate how the interaction between these permeability barriers could cause either a complete rupture or the occurrence of slow slip events and a seismic creep. So here you can see some of these results where basically by changing the size of the seismic patches compared to the barriers, we can either have a case where we have a complete rupture, meaning that the seismic event is nucleating and then is capable of jumping this barrier and have a complete rupture of the fault. In this case, instead, we can have that the barriers are sufficiently strong to prevent a complete rupture, and we have a cascade of seismic and aseismic slip. So in this case, we have the nucleation of one event, then is propagating, then is arresting, and then is progressively jumping through these barriers, and finally we can reach the left and the right side of the fault. When these barriers are even more stronger, we typically observe the nucleation of slow sleep events, and they never increased and dynamically switch into a dynamic rupture. While when these barriers are even stronger, we typically observe a stable creep. We try to study this problem more in detail and exploring the parameter space by changing the width of these seismic patches compared to the barriers where the permeability is very low. And we try to keep constant the so-called nucleation size, which is here in this symbol L sub C. So in this case, you can see that when the seismic barriers becomes larger and larger, then we can end up in this domain when we can have where we can have a seismic full seismic rupture. And here within this domain, we can have this so-called cascade of seismic and aseismic sleep, while moving towards smaller seismic patches compared to the size of this barrier, we end up with slow sleep events and creep. We also try to perform a different type of simulations. This is another study where we account for a vertical antiplane motion. So simulating a vertical like sleep fault. Here you can see the depth distribution of the rate and state frictional properties, but we also try to account for the evolution of permeability by taking into account the evolution due to the effective pressure, and which is basically simulating the closure of the fault with the effective pressure, and the evolution with the sleep rate and the healing time. In particular, this evolution, permeability evolution law, had been proposed by the study of Zhu et al. In 2020. And in the case of the evolution of permeability with the sleep rate and healing time, we have that the sleep rate is associated with a characteristic sleep weakening distance, and which defines our weakening of permeability, and the other term which instead describes the healing, where we have 1 over T, and T represents a characteristic healing time. Of course, we have very poor constraint on this, particularly this L and the characteristic healing time, and we try to explore how these two parameters can affect the evolution of permeability, and how they can control the occurrence of seismic and aseismic sleep within the same fault segment. So here you can see an example of this type of simulations where we can observe a pretty interesting behavior of seismic and aseismic sleep within the same fault zone. This is because every time we have a seismic event, the increase of stress could cause migration of pore pressure because the permeability increases, and we can have the propagation of a slow sleep pulse before the nucleation of another seismic event. So in this case, by accounting for the dynamic evolution of permeability, we can observe seismic and aseismic sleep within the same fault segment, even including a nucleation size that is relatively large compared to the size of the fault. And because of that, we observe this type of behavior where fluids are triggering a slow sleep transient, and eventually we can have the propagation of seismic events. In this second part of the presentation, I would like to discuss some of this this type of results by accounting for a different plasticity model. So here, instead of accounting for the classic rate and state friction, we are instead assuming a rate strengthening friction. So in this case, we are taking into account a formulation where we still have the so-called direct effect, which is controlled by the parameter A, typically using rate and state to simulate the direct effect, which is a feature that has been confirmed by laboratory experiments. And the weakening phase is not controlled by the evolution of friction and the state variable, but is controlled by pore pressure, which decreases the effective pressure, and because of that, we can have a dynamic instability. So in this case, we can have a formulation that looks like this, where we have the ratio between velocities, the slip rate, and the characteristic slip rate, and then we have A defining the direct effect over our static friction. So as you can see, in this case, our mu0 is not changing over time because the dynamic weakening is controlled by the fluid evolution. So we try to test this type of plasticity model in a very simple strike slip setup. This is compared to the previous setups. This is an in-plane shear motion where we have a fault with a finite width. We impose an inflow and outflow of fluid, and we impose a constant loading rate from the top and the bottom. And we assume a rate strengthening A that is higher on the left and the right side of the model, and lower, similar to the classic A that is used for velocity weakening in the center of the fault. So here you can see an example of the evolution of seismic cycles with this type of plasticity model. And you can see that when we have an event, the slip rate is, of course, increasing close to meter per second, and then is coupled with the decrease of time step, and the pore fluid pressure is increasing, which causes a decrease in the effective pressure, which is here described by the difference between the total pressure and the fluid pressure. And here you can see a propagation of a seismic event, and we are plotting here the horizontal velocity on the fault, but also in the bulk of these simulations. In this case, you can see that we have a couple system between the evolution of pore fluid pressure. So when we have an event, the pore fluid pressure is increasing, and at the same time, shear stress is decreasing, and the viscosity drops of several orders of magnitudes from the point where we have the nucleation of an event to the propagation on the left and right side of the simulation. So we have this coupling between the decrease of viscosity, pore fluid pressure increase, because we have also the compaction viscosity that is decreasing. Then we have a drop in the strength, and this localized even further on the fault zone. With this type of simulations, we try to explore the initial pore fluid pressure by assuming either higher or lower initial pore fluid pressure. And you can see that in this case, we can have seismic events that are nucleating from one side of the model and propagating to the other side. And this is the evolution of this type of simulations with this black line. When we already assume from the beginning a high pore fluid pressure, the system becomes more unstable in the sense that we can have slow slip events and seismic events within the fault, within the same segment of the fault. And this is mostly controlled by the pore fluid pressure that we have right at the beginning of each event. And in the case of lower or higher pore fluid pressure, we can end up with a seismic event or a slow slip event. The most interesting part of this type of dynamic instabilities is that they are controlled by the evolution of pore fluid pressure, and therefore the propagation of these events are driven by solitary pore pressure waves. Here you can see an example of a seismic event. So we have here the nucleation and the propagation from one side to the other side of the model. With this type of simulations, we can keep track of the evolution of compaction, the solid compaction within the fault zone, and the fluid pressurization. And you can see that from the nucleation point, we have this propagating front of solid compaction, which is immediately counteracted by fluid pressurization. So here with these lines, you can see these 8 profiles that we try to plot in this panel. And so from this figure, you can see that we can have the nucleation of an event where we have the compaction of the solid matrix and the fluid pressurization. So one mirror the other. And we have the propagation of a pore pressure wave where the solid compaction is immediately counteracted by fluid pressurization inside the fault zone. The efficiency of this mechanism is strictly controlled by the compressibility of the solid and the fluid constituents. We have typical values that we are assuming for the compressibility of the solid matrix and fluid. In particular, we assume the classic value for pure water. And so based on this mechanism that you can see from this sketch, we can have a shearing event which causes a compaction within the fault zone, and then this is immediately counteracted by the fluid pressurization within these pores. So we try to explore this problem by changing the solid compressibility and the fluid compressibility. This is a case that can be mostly related to the presence of fluids with different compressibility, such as supercritical CO2, which can change the compressibility of fluid by up to 2 orders of magnitude. And so we try to explore this problem by changing the porosity from 1% to 10%. And here you can see the evolution of this type of events, where we can either have seismic events when the compressibility is low because this mechanism is very efficient. And then we transition towards slow slip events and stable creep. And here in this case, you can see that the pattern is still very similar, but the window where we observe slow slip events tends to be higher, simply because for higher porosity, we can also observe a stronger compaction of the solid matrix. In general, these figures shows that this behavior is strictly controlled by the compressibility of the fluid component. And this has implication, for example, for the reactivation of faults in the case of CO2 sequestration, where the compressibility of the CO2 can be very different from the one of poor water. Now, one of the key points that I would like to discuss is also the competition that we can observe between dilatancy and compaction. We have evidence that during the shearing phase, we can have an initial increase of pores, which increase the volume and therefore can decrease the effective pressure within the fault zone, which can be described by this phase where we have a front of a seismic event, and we can observe a dilation effect, which is causing a decrease in the porphyry pressure. After that, we can have instead a compaction effect, which can instead increase the porphyry pressure within the fault zone and can allow the rupture to propagate for longer distances. We are now trying to explore this problem and trying to derive a linear stability analysis in order to understand the competition between compaction and dilation. And the results so far are telling us that there is a critical dilation where the compaction can either overcome this dilation effect and still trigger a seismic event, or in the case when dilation is strong enough, can prevent the nucleation and the propagation of seismic events. Now, if you go back to the point of subduction zones, we have observations that we have a depth varying slip behavior from earthquakes to slow slip events. And this is just an example that we have in Cascadia, where we have the coupling map showing the seismogenic zone, and then this band of cumulative slow slip over 10 years of slow slip events. And so when we think about this problem, we can assume that the percolation of fluids due to dehydration can cause an increase of porphyry pressure, which can then control the behavior of either seismic or aseismic slip. So we try to explore this problem with a very simple model where we have a wedge-like setup, and we try to change the permeability within the fault zone by assuming a constant permeability or a permeability that decreases with depth. And we try to understand how the presence of this depth varying permeability can control the occurrence of seismic events and slow slip events. Here you can see an example of this type of simulations when we assume constant permeability, and the model results in complete rupture within the megatrust with the recurrence time that are quasi-periodic. And so you can see that we have a sequences of seismic events with regular interseismic, quasi-regular interseismic periods. The interesting results are that when we assume a depth-varying permeability, this could cause a depth-varying pore pressure evolution. And because of that, we can have the premature nucleation of seismic events at the bottom of the seismogenic zone. And because of that, we can observe a cluster of events with different size, from a partial rupture at the bottom of the seismogenic zone to larger events composed by an event and then an aftershock a few hours later, like in this example. And because of that, we can have this variety of small and large events within the fault. And here you can see, for example, the evolution of fluid pressure over several cycles. And you can see that at the bottom of the fault, because of the low permeability, the pore fluid pressure tends to be chronically high, and therefore we end up with this cluster of events with different size. Finally, the last slide that I would like to show for this presentation is related to the spectrum that we can observe in terms of seismic and aseismic slip. This is something that has been explored in the rate and state friction, and we try also to understand whether this can be simulated also with this rate strengthening behavior. And we try to perform a series of different experiments where we change the permeability on the fault and the porosity. And the results shows that within a certain window that you can see here with these purple dots, purple circles, we have seismic events. When we move towards lower permeability, like in this point C that we have here, the permeability is lower, pore fluid pressure tends to be higher over time, and we typically observe a slow slip events. When the permeability is even lower, what we observe is the decay oscillations, meaning that pore fluid pressure is always high, and there is no recovery in time within the fault zone. And the first event is followed by another event with a slower slip rate, and so on and so forth. And we end up with a stable creep after a series of 4 events here. When the permeability is instead too high, we simply don't pressurize fluids within the fault zone, and we don't have any seismic event. It's interesting to observe that this transition between seismic events and slow slip events here is characterized by this transition zone that is controlled by the constitutive relations that we have between permeability and porosity, where here you can see that the reference permeability over porosity and the reference porosity is over an exponent n, which in our simulation is 3, and this confirms the transition that we observe in this slip spectrum. On the other hand, we observe that we have a sharp transition here for a higher permeability, and at some point we reach some kind of like a permeability threshold, and above this value we don't observe any seismic event. So to conclude this presentation, we saw in the previous slides that fluid-driven instability in the case of a rate strengthening plasticity formulation are fundamentally different from the one that are controlled by rate and state friction, in the sense that they are mostly controlled by the compaction and decompaction within the fault zone, which can cause a dynamic self-pressurization and an instability in the form of a solitary pore pressure wave. This mechanism is particularly efficient when we assume a fault with undrained condition, where the evolution of pore fluid pressure within the timescale of nucleation does not allow fluids to escape from the fault zone. And the hydraulic properties also control the slip behavior, in particular porosity and the permeability. And because of that, we can either have slow or fast events, even within the same fault segment. And we have seen that we can have different mechanisms that are operating at the same time within the fault zone. An example is dilation and compaction. But in general, for a given set of parameters of poroelastic constant, in particular Biot and Skempton coefficient, we usually observe that compaction can overcome the initial phase of dilation and can still cause a seismic event. And in general, this type of study are also giving us some more information on the hydromechanical structure of faults and how it's important to also include them to study sequences of seismic and seismic slip. Thank you for your attention.